Today we'll discuss practical evaluation strategies for compound AI systems. Here you can find the slides of our presentation. And while you're scanning a short announcement, we have a bunch of data science themed sticker packs. Therefore, if you would like to grab one, feel free to approach us after this talk. Okay, so let's start. According to McKinsey March 2025 global survey, more than 3 out of 4 organizations are now using AI in at least one business function. Given such a huge shift, it's somewhat safe to say that we are well past the experimental stage and AI is now part of mainstream business operations. Such widespread adoption can have a lot of impact on productivity, decision-making, and competitive advantage, but might also add hidden risks. The reason for that is the fact that LLMs are not deterministic. The same input can lead to different answers depending on randomness, context length, temperature settings, etc. Additionally, the tasks being solved are often open-ended. Instead of a single correct output, there might be multiple plausible responses, making evaluation more complex. On top of that, complex AI systems usually have multiple dependent components. For example, a retrieval, a chain of model calls, tool usage, etc. A small miss in any of those components can snowball into a major error, which means that without proper evaluation, you may be shipping changes without knowing whether you're improving the product or making it worse. Given the unpredictability and complexity we just discussed, it's clear that evaluation isn't optional but foundational. We need robust evaluation systems that can operate in real-world conditions, track performance over time, and guide the improvements. In the rest of this talk, we'll explore practical strategies to design, implement, and scale such evaluation systems. But before continuing, let's figure out which evaluation types are there in general and which ones we are going to focus on today. First of all, there are plenty of quantitative metrics like price, latency, etc. They're important for performance engineering, but we are not focusing on them today. Instead, we are more interested in qualitative evaluation, assessing whether the model produces helpful, faithful, relevant outputs. But obviously, there are many different types of qualitative evaluations as well. To structurize them a bit, we can imagine a plane with 2 axes: complexity and time or effort. On the low complexity, low time end, we have generic NLP metrics like BLUE or RUGE. They are fast, but are often poor proxies for real-world quality and have relatively low correlation with human judgments. Next are standardized benchmarks like MMLU or Helm, which are still very broad and likely not sufficient for domain-specific use cases. Therefore, our focus is now on the top right corner, domain-specific evaluations for reference-free tasks. They require a lot more to create, but measure what actually matters. At this point, it's crucial to establish something that is very obvious, but at the same time, something that is often overlooked. In order to create a domain-specific evaluation, it's crucial to have someone with a deep understanding of a given domain, a subject matter expert or SME. Only an SME can subtly mistake that generic benchmarks or even experienced AI engineers can completely miss. Therefore, when starting a project, one of the first questions you should ask: who are the SMEs and where would I find them? Once you come up with an answer, the next logical question could be: should I involve one or several SMEs? With one domain expert, you get a single, consistent standard for evaluation. It's faster, decisions are made quickly, and there is less coordination overhead. But relying on one person also means you're exposed to their personal biases, and you might miss perspectives that matter to different user groups. Whereas involving many SMEs broadens coverage, you get different viewpoints, biases can balance out. However, the trade-off is that multiple SMEs introduce variations in how outputs are judged. It also takes more time, you need coordination, some process to resolve disagreements, etc. It's entirely up to you which path you want to take, but more often than not, it makes sense to start with a single SME and then consistently expand to multiple once the project matures and scales. Once you get an SME, the first thing you can start defining together are assertions. These are automated checks that verify specific properties of your system's output. They are fast to implement and can run continuously without manual intervention. Even a handful of assertions can already improve reliability by catching some obvious failures. One type of such assertions are deterministic rule-based checks that are perfect for objective and ambiguous conditions. For example, making sure the response is valid JSON, verifying formats like URLs, dates, ensuring that no banned terms appear in the output, and so on. For example, in this code snippet, we can see the simplest form of a code-based assertion. We send a fixed prompt, what's the capital of France, to the model. Then we check if the return string matches the exact expected output, Paris. This kind of test is deterministic. The same correct answer will always pass, and any deviation will fail. However, code-based assertions are not well suited for open-ended quality checks. In contrast to code-based checks, LLM-based assertions use another model, sometimes even the same base model as your AI system uses, to evaluate outputs. This is useful when the criteria are subjective or complex, and we can't easily write deterministic rules in code. For example, for validating that response has a professional tone. In principle, we can use assertions in two distinct ways. First, as guardrails at runtime to block unsafe or invalid outputs. That's not something we focus on today. Second, as unit tests that we can run, for example, in CI pipeline to check for regressions. Importantly, we should not cover absolutely everything by tests and think of them as some sort of a score. Instead, only the minimal acceptance criteria should be covered. So if the test fails, we know that there is no point continuing with further evaluations. Consequently, we want all unit tests to pass in all cases. However, given the non-determinism of LLMs, some cases might still fail from time to time, and therefore it's possible to define a soft pass threshold and check those failed cases manually. While unit tests give us quick checks on absolute must-haves, they don't tell us much about the overall performance of our AI system. That's where model evals come in. When we move from unit tests to model evaluations, the very first thing we need to create is a data set organized along three axes. Features, those are AI system capabilities we want to test. Scenarios, they capture the contexts where those capabilities appear. And personas, they represent the intended style or perspective for the output. To make this concrete, here are some examples of what might go into each axis. Features could be summarization, database lookup, information retrieval. Scenarios could be that there is no information available in the database, or user provided incorrect data, or several results were found for a single query, and so on. Personas could be just different types of users making the request. By mixing these three dimensions, we can create diverse and representative cases for our evaluations. In early-stage projects, it may be difficult to come up with sufficient amount of cases manually. In that situation, we can use LLMs to scale up this amount to a significant number by providing the model with the description of what features, scenario, and persona represent, and asking the model to generate possible combinations of such triples. However, keep in mind that some of this combination might be irrelevant, therefore they still have to be checked by SMEs. Once we've defined our features, scenarios, personas, we can select the samples covering these dimensions to form a structured dataset. Again, if there is not enough real data available, we can generate synthetic cases using LLMs. Once the dataset is ready, we can run it through our AI system and collect the outputs. As shown in this table, now we have the diverse input queries covering various scenarios and final outputs that our AI system produced. And obviously now we want to get an idea how good those outputs are. There are a few ways we can do that. Earlier we already talked about assertions and established that they are mostly good for fast and simple checks. That's probably not something we need here. Maybe we can use generic LLM-based metrics, asking a critique model to score the response quality, but those are often too general. Traditional supervised metrics are also unlikely to work as they are not suitable for open-ended tasks. Which brings us to a conclusion that the most accurate evaluation is the one done manually by SMEs. However, to ensure efficiency, the evaluation must be guided by a well-structured framework. With that, I would like to hand it over to Oleh, who will dive deeper into how to build such evaluation framework.
So when you start working on evaluations, there are several questions that naturally arise. One is whether to use a single overall metric or break it down into multiple metrics such as accuracy, completeness, and so on. Another one is the choice between a Likert scale, for example, 1 to 5, or a binary pass-fail. And the last one is to how to structure the process to get most out of it. And arguably, the most efficient approach is to have the SMEs give one binary metric, pass or fail. And there are actually several arguments to support this claim. First of all, such approach forces clarity. Either something meets their acceptance criteria or it doesn't. It's also faster for the SMEs because they don't really have to think whether something is 3 or 4 on a given scale. And by extension, it also reduces inconsistencies because different SMEs wouldn't interpret for example, 3 differently. Finally, it's easier to aggregate in an interpretable way because the pass-fail rates can be summed into a clear percentage pass rate. As an addition to the pass-fail verdict itself, it's also beneficial to ask the SMEs to provide the natural language criticism of their reasoning. For example, if an output fails, SMEs should clearly explain why it didn't meet the acceptance criteria, referring back to the defined acceptance criteria. This is why it's easy to capture what exactly went wrong. And even if something passes, usually there is still room for improvement, and it's good to have it noted for future refinements. Optionally, it's also possible to ask the SMEs to provide the correct answer itself. It's always beneficial to have one. However, at the same time, given the complexity of the task, it might be very time-consuming. So at this point, we have all of the pieces in one place. For each sample, we have an input to the AI system, the output it produced, the score from the SME, and the explanation of the SME's reasoning. But at the same time, we didn't do anything to optimize our system to improve the score. And unless we were very lucky, the evaluation would uncover a lot of hidden issues. Therefore, it would be a good idea to do something about that. And here, the process resembles traditional machine learning in many ways. We can split our data set into 80-20 or 50-50 subsets, and iteratively resolve the issues by adapting the AI system itself and extending the unit tests and assertions to catch similar problems in the future. Now, during those optimization iterations, when deep diving into issues, it's very important not to forget that we are not dealing with a single monolithic system, but with a compound one. That means we don't just have a single input and the output, but we have lots of steps. Therefore, the real insight often comes from examining the intermediate results. For example, what was retrieved or which reasoning steps the LLM took. And in order to do that efficiently, we can incorporate tracing into our experiments. So a trace is essentially a record what happens when the system processes a request. It captures every step and shows how the data flows between the components, making it much easier to see where something went wrong. So it's very important to have a user-friendly interface to quickly and easily diagnose and identify the steps that caused the failure. But once we did several iterations of system improvement, we are finally ready to deploy our system into production. So does it mean that our work here is done? And not really, because we shouldn't forget that it's also necessary to evaluate and monitor our live system as well to ensure that it still continues to perform well on new unseen data. Obviously, we can follow the same approach as during development, collect the data and let the SMEs evaluate it. However, at this stage, the data volume increases and SMEs processing capacity might become a real bottleneck. To overcome this bottleneck, the evaluation process can be automated by using an LLM-as-a-judge. As follows from the name itself, we want to use an LLM that predicts the scores that would otherwise be produced manually by the SMEs. So now the ultimate goal is to somehow align the LLM judges' scores as closely as possible to the human ones. There are actually lots of different approaches to create LLM evaluators. We don't really have time to check all of those, so let's have a look at just one very popular method called geval. It consists of two steps. Firstly, the task introduction and the evaluation criteria are created and passed to the LLM to generate a detailed chain of thought of the evaluation steps. And then these evaluation steps are concatenated with the main prompt and the score is returned. It's also possible to sample the response of the judge multiple times, say 5, and take the average in order to get a more representative answer. So hopefully, after several iterations of improving our judge, it's stable, well aligned with the SMEs, and we reached our convergence criteria. So it doesn't mean that we can take this judge and completely replace the SMEs. Okay, and the short answer is no, because even the best LLM judges are still only the approximations of the SMEs decision, and they won't always be right. So SMEs assessments are still the gold standard. Also, we need to remember that LLM judges are AI systems itself, and usually we don't monitor those AI systems with yet another automated AI system. So if it degrades, we might not know unless the SME checks. SMEs are also needed when new types of data or new features are introduced because the judge hasn't seen them before. So overall, SMEs still need to review the data, but with a judge in place, they can only check a smaller subset of traces and do it less frequently. Now the question is how to approach this manual analysis of the traces in a bit more structured way. So SMEs can start with checking some random traces and writing a brief description of what was observed. For example, if the outputs are incorrect or the overall behavior of the system just feels wrong. However, at the same time, this doesn't provide enough of actionable insights, as one would need to keep a very large portion of information in mind just to understand the big picture. Hence, it would be nice to somehow aggregate this information. First of all, we can group the annotated cases according to the failure types. The failure type should be defined as a binary flag. Either a failure type applies or it doesn't. It's not necessary to come up with those group names manually, but we can also delegate this task to an LLM. And when we have a list of occurring failure types, we need to classify each trace. To save time, it's again possible to employ the LLM, which would do the preliminary label assignments. This way, the SMEs don't have to do everything from scratch, but just validate the correctness. Finally, we can aggregate everything into a single overview table. That way, we can identify high-frequency failures and decide whether we need to prioritize them first. So let's recap what we discussed so far. First of all, and most importantly, the evaluation of domain-specific systems is hardly possible without having a subject matter expert. You should find an SME as early as possible, and it's totally fine if you only have one. Together with an SME, you can start by designing the assertions, which should be used as minimal acceptance criteria, and then you can move to actual evals. For the evaluations, focus on a single binary metric and try to optimize your system to maximize that metric. Once your system is stable and deployed, your job is not yet done because you need to monitor your system in production for degradations. Here, the LLM-as-a-judge comes into play, but it doesn't completely replace the manual assessments by the domain experts. So, in conclusion, I would like to say that the work on the AI systems never ends. They need continuous refinements and monitoring. So, having a well-established framework is crucial in order to make sure your product improves and delivers value. Today, we tried to demonstrate one such framework, but given how novel and fast-paced this domain is, probably there is more than one way to do it correctly. Therefore, if you have some thoughts, experiences, or general ideas regarding this, we would be happy to talk to you during one of the coffee breaks. And this is almost it from my side, but before finishing, I wanted to make a small remark that the UI screenshots we were using in the presentations are from the Data for Studio, which is a new open source MLOps and LLMs platform that we are currently developing. And we would really appreciate if you try it out, provide your feedback, or maybe just start it on GitHub. And now that was it from us. Thank you for your attention, and we are ready for the Q&A.
Thank you very much. So we have two questions in the app. Okay, the first one, have you considered adversarial users as a part of evals dataset you want to create? Example, users trying to game a system, get a refund, etc., or users trying to jailbreak the LLM?
Okay, I'm not really sure I understand the question correctly, but if I got it right, the idea is to incorporate the user's feedback into the evaluation system itself. Obviously, you can do that, but probably you cannot start with that because at the beginning you don't really have enough of the user's data.
Yes.
Sorry, I think maybe the idea wasn't expressed, but I was asking about adversarial users, so
okay.
Users who are trying to jailbreak the LLM or users who are trying to game the system. And had you considered using those as part of your initial assertions or for part of your synthetic data set creation when you're trying to come up with some like expressive inputs to test your system?
Okay, so there I would say it really depends on the use case, because in some of the use cases you wouldn't expect your users to jailbreak your system. For example, if you're using it for an internal chatbot or something like that. So in this case, I think it's not really necessary, but overall, this framework is rather generic. So yes, you can define your assertions or evaluations or synthetic data to account for those attempted adversarial attacks. So yeah, you can do that.
You have them. What one would you like to ask?
Oh, sure. Sorry, does anyone else have questions? I think I'm the only one who put them in. The other question I had was about LLM judges and how do you form an opinion that it's good enough to use against production data? And I was also asking about confidence levels, like is it possible to get the judge to output a useful confidence score that you could use to like define a production quality threshold?
Okay, so let's take it step by step. Regarding the threshold where you're confident enough that you can use the judge in production, you have this alignment score, so how often the judge produces the same result as the SME. So you should define this threshold yourself, but you should you should do it based on that. Regarding the confidence intervals, in principle, it is possible to ask the LLM judge to produce the confidence. I don't like this idea at all because I think it doesn't really correlate with the actual confidence of an LLM. Therefore, what I usually recommend is to sample the output many times, maybe with the higher temperature, and then check how many times it was, let's say, true and how many times it was a false, and this can be used as the confidence.
Oh, yeah. Thank you for insightful talk. So I wanted to ask about stability of the testing LLMs. So I think in one of the slides you mentioned that it's difficult to write tests for LLMs because the answer is undetermined.
Yes.
But I assume that if we would query LLM with temperature 0, then it will behave like a determined system, and so therefore tests could be written, for example, for LLM answering temperature 0. So what might be the pitfalls of this approach?
Yeah, it's a good question. First of all, sometimes you don't really want to have temperature 0 for your LLM, for example, if you want to have a creative task. But even if you are okay with having a temperature 0, it's not well documented, but for example, ChatGPT is not completely deterministic even when the temperature is set to 0. That's the first drawback. But also some of the newer models, for example, the reasoning ones, they don't support the temperature parameter, so you cannot really do that.
Thank you. Any other question here? So there is, do you have? Yes.
One question as well, but I'll just say it out loud. How do you select, after you've gone through a few iterations of, for example, finding issues with SME, and you've kind of found a bunch of different problems in your samples, and you want to refine, add more, how do you find the new samples in a way that ensures that you're sampling the state, like the sample space, in a way that you're not just focusing on some very repeatable issues and you're
okay, so I'll try to rephrase the question and then you can say whether it's correct or wrong. But basically what you are saying is that when we did the improvement, it's better to have a new sample to evaluate it on. Yes, it's always a good idea to have it this way. In this case, you can do almost like I forgot this term, but basically how you do it in time series. For example, you have one chunk for training, another for evaluation, then you use this one for training, this one for evaluation, and so on and so on. But more often than not, we don't really have enough of this data, therefore we just split it into, let's say, train and test subsets. You do all of the improvements on this train set, and at the very end, only once you evaluate it on the test subset to make sure you didn't completely overfit.
I kind of went more on the, of course you'll separate into train and test, but over time you might find that your LLM is not catching a number of issues and you want to kind of improve it and sample the state of the different samples that you have in your training set to make sure that it's varied enough.
Yes, so basically that's why you have to monitor your system during production, because this way you also collect new data, you group this data into the failure types, and with time you can append your training and test sets with that data. Okay, hopefully it answered the questions. If not, then let's talk about it later.
Thank you. Any other question, please? Raise your hand. Okay, we are almost on time.
Yes, thank you.
Thank you very much, Oleh.
Don't forget about the stickers. If you want to have one, please come.